Well, okay, it's recording. Welcome all to the Austin Python Meetup. Unfortunately, we cannot meet in person, but we are meeting online, and there's a bunch of us online interested in learning things about Python. We will have something related, semi-related to the pandemic itself later on in the show. But for now, I'm gonna present our first speaker and afterwards second. Our first speaker is Derek Drummond. He's going to talk about solid principles of Python, solid design principles. It's something that he'll tell you later. It's something that came from C and now applied to Python. So this will be the first talk. The second talk will be by Ivelin Ivanov. He will be talking about all the home automation, with this home automation, there'll be something related a little bit to the pandemic. And again, things related to Python in both talks. So without much ado, I'm gonna hand it over to Derek. Derek, can you please unmute yourself and present yourself and then share your presentation. I'm going to mute myself now.
Awesome, appreciate that. Hi, I'm Derek. I have a slide in my presentation, so I'm just going to go ahead and share the screen real quick. And you all will, oh, never mind, y'all. Well, maybe y'all can still see me, but you should see my screen. But if you see me looking down, it's because I have to do my notes on my phone. Otherwise, you would see my speaker notes, and those are, top secret, G14 classified. So I'm going to cover a Pythonic guide to solid design. But first, let's do the obligatory narcissism. I'm sorry, I should be presenting it. So I have this slide because every presentation I've ever seen always has one about the presenter. So I'm a clean code advocate, which is where the solid design comes from. I'm a polyglot developer, so I can write any of those languages listed. It's not uncommon for me to write code in C#, PHP, Python, and JavaScript in a single day. I am a co-host of the Namespace podcast, and if you like this talk and you want to have more content like that, please follow us on Twitter and subscribe to the podcast on any of your favorite podcast apps. So I'm also the author of a Pythonic guide to solid design principles. This presentation actually gave rise to the article. So any reason that you don't want to listen to my voice, if it's just grating, I get too boring, feel free to mute me, and you can just go read the article on Dev2 later on. And that is my Twitter handle in case you want to follow me there and ask questions. So the solid design principles are 5 principles that were originally presented by Robert C. Martin, more commonly known as Uncle Bob, and they were presented in his paper, Design Principles and Design Patterns. I can share the link on the Meetup page if you actually want to read that paper. But the actual mnemonic of solid came from Michael Feathers, and he took 5 of those principles and he ordered them in a way that, of course, spelled what you have here. So we're going to cover those all in a little bit more detail, and we're going to cover them in order, but you have the single responsibility principle, open close, Liskov substitutability, interface segregation, and dependency inversion. Those are the 5 official rules of solid design. And to do this, we actually have to have a definition of Pythonic. And much to my dismay, because I'm still fairly new to Python, like within 2 years, there doesn't seem to be an official definition of Pythonic, but there is an unwritten understanding of Python. And the best I was able to come up with through some quick Google searching is above correct syntax, Pythonic code follows the normally accepted conventions of the Python community and uses the languages in a way that follows the founding philosophy. Pretty much every definition kind of guides you to that point. I think the best example of the founding philosophy is, of course, the Zen of Python. This was written by Tim Peters, and it was proposed, it's actually part of the Python standard library through PEP 20. And the fun Easter egg is, if you import this in your scripts or in a Python REPL, you will actually get the Zen of Python printed to your screen. So we're going to use these Zens throughout the talk to relate the solid design principles to the Zen of Python. And there's one last thing that I want to do, and this is my frustration with solid tutorials, is they all use a different code snippet for every principle. I want to take a single code base and I want to make it more solid as we go through each principle. So this is going to be our starting code. It's pretty simple. You see we have an FTP class. Under the hood, you have an FTP client or an SFTP client, and you can upload files and you can download files. Overall, it's pretty good abstraction. I think most of us would agree, but let's see if we can make it a little bit more solid. So we're going to start off with a single responsibility principle. The official definition is every module or class should have only one responsibility and therefore only one reason to change. Oh, jumped ahead, a little too quick there. So to me, the single responsibility principle is all about increasing cohesion and decreasing coupling by organizing your code around responsibilities. And you can equate a responsibility to a use case. So each module should have a single use case. The relevant Zen there, I think, is there should be one, and preferably only one, obvious way to do things. And it's not a big leap to see how modules with a single responsibility lead to this. So to quote from my favorite MASH character, Charles Emerson Winchester, I do one thing at a time, I do it very well, and then I move on. So if our module has a single responsibility and handles that responsibility very well, there's not much need for another module to handle that responsibility. So a lot of times you'll hear the single responsibility principle explained as each module only has one reason to change, which can be a little frustrating, I think, because the definition of reason to change is kind of loose. So when you're thinking of reason to change as a responsibility or a use case, the only reason the class or module is changing is because its use case has changed. So given that, we can identify a couple of violations with that original code, which was the FTP client handles two use cases: uploading files and downloading files for FTP and SFTP, which are two different things. Both of those also have a different underlying protocol. FTP is more similar to HTTP, while SFTP is more similar to SSH and SCP. And then in the original code, you'll see in the init function, you have the FTP driver and the SFTP driver. Because those are separate things, they can actually change independently of one another. And so if the underlying driver changes, this class now has a reason to change. So the way to solve that is to split up the functionality into two classes. And right off the bat, I think this just looks far more Pythonic. The code is sparse and not dense. It's simple, not complex, and it's flat instead of nested, and all of those are parts of the Zen of Python. So now our FTP client only has one responsibility: the upload and download of FTP, or to an FTP server, and the SFTP client only has one responsibility, which is the uploading and downloading of files to an SFTP server. That encompasses any driver changes, security patches, or changes to the underlying protocol itself, although that is kind of like a rare case, but I'm not going to exclude it from happening. So next up is the open-close principle. Its official definition is software entities, which are classes, modules, functions, should be open for extension, but closed to change. And this one really caused me a lot of headaches because extension and change had such similar definitions, and they're not talking about, is it a code change? Because technically an extension is a change to your code. And so without a good in-depth explanation, I think this one can really confuse people and be very overwhelming. I think it's far more intuitive to think about this as function signatures. Or, as I like to say, it's easier to add something than it is to take it away or rename it. And that goes for parameters in a function signature, or functions in a class, or features in an API. It's just easier to add something than it is to take it away. So if we're going to talk about change versus extension, I think there's a couple of really helpful examples. So for a change, that's something that's going to force calling code to be updated. And examples of that is renaming the function, reordering the parameters, and adding non-default parameters. Whatever calls the function that you've just modified is also going to have to change. So you've changed the behavior of whatever entity you were working with. An extension, on the other hand, is something that doesn't force calling code to change. So that's renaming a parameter because that's only used inside the function. It doesn't change how the code calls it. Adding args or keyword args, those are things that get defaulted in Python itself, so they don't break calling code. Or adding a parameter but giving it a default value. All of those things can happen, and whatever code called your function is blissfully unaware of that change. And that's really what we're trying to get at for an extension. So, given those definitions, let's take the use case of having to add bulk support for our upload and download functions. For me, the gut reaction was, we'll add a bulk upload and a bulk download function. And fortunately, that is also the solid way to handle this use case. So here I'm just showing the FTP client because that's the only place that I have to add this code. And you see there, all it does is loop through the files, calls the upload function, and then in download bulk, again, loops through the files, downloads them, adds them to a list, and then returns the list. This is an example of extending the class. Whatever code was using upload or download no longer has to change, unless their use case of doing a bulk upload has changed as well, and in which case that's back to the point of extending your code. The cool thing about this, and the way the FTP client, SFTP client were structured, is SFTP inherited from the FTP client, so upload bulk and download bulk only had to be added one place. And I threw that in there for everybody that's a big fan of the dry principle. It's not a solid design principle, but I know it's got a lot of popularity, and I've heard it a lot in the Python community. So this brings us over to Liskov's substitutability principle, perhaps the most difficult to pronounce and maybe the most difficult to understand as well. I was really fortunate in my computer science classes. This is the only one I actually learned of the solid design principles, and it might be why this one was so intuitive for me. So the formal definition, which was proposed by Barbara Liskov back in 1994. And let's just take a moment. Female developer back in 1994, and she's made contributions that you're still hearing about today. But her formal definition was, if S is a subtype of T, then objects of type T may be replaced with objects of type S. And that is a pretty rigid definition, but difficult if you're just learning about inheritance and typing. and especially difficult with Python that does duck typing, because you don't have to have a strict inheritance hierarchy for duck typing to still do its thing. So my informal definition of this is any child class can replace its parent class without breaking functionality. So that's my layman's term explanation of Liskov's. So it still leaves the flexibility for Python's duck typing, but it still captures what Liskov's is supposed to do for you, and it's strictly a parent-child class relationship, not duck typing side-to-side type of a relationship. This one, I think, has the perfect relevant Zen of Python, which is special cases aren't special enough to break the rules. And that's really what a subclass is. We have our base class. We've come to a point where we have a special case, and we need to extend that, so we inherit from it. But our special cases shouldn't break the rules. So however it's implemented, it should replace the base class without breaking any kind of functionality. So looking at the previous code, our SFTP client was a special case of FTP, which is why it inherited from it. And it's also why I only had to put upload bulk and download bulk into FTP, because the signatures for the upload and download function were the same, and those two bulk functions just called them. Python's inheritance brought those functions down, and then when it made its call, the resolution was to the SFTP upload and download functions. And so that was intentionally done so that when we got to Liskov's, it would make sense. But there is another case of a special edge case for FTP, and that's FTPS. And yes, for everybody that's asking, FTPS and SFTP are actually different things. So if we're going to add that following Liskov's, all we have to do is throw the class in with the constructor that sets up the FTPS driver, pass in all the right parameters, and then it will actually inherit the upload, download, upload bulk, and download bulk functions and work totally fine. We don't have to repeat any of that code. So if that doesn't blow your mind, give me a few more minutes to get through the next two principles, and we'll see if we can impress you a little bit more. So interface segregation is no client should depend on methods it does not use. To me, the relevant Zen is readability counts, and complex is better than complicated. So unfortunately, unlike Liskov's, I didn't learn about this at university, and it was the last, and for me, the most difficult to understand. And a little bit of that is because of how the solid design principles are presented. You almost always see it with languages like C# or Java that are static, strongly typed languages. And they both have an interface keyword. And so people like to say that interface segregation is about defining these interfaces. And so that caused a lot of confusion to me. And I'm hoping that I'm going to solve that for all of you over the next few minutes. So the other issue that you'll see when this principle is explained is people think that tiny interfaces, and those are interfaces with like a single function in them, is following the interface segregation principle. And I think that's like okay, but I think we can do better, and I think we can do better especially with Python. But you're gonna have to bear with me for a few minutes as I share some C# code. So please nobody jump off the call at this minute. So here's some C# code with a typical implementation of the interface segregation principle. You still have the FTP client, it still has an upload and a download function, but it implements the I can upload function and the I can download function, or I'm sorry, interfaces, not functions, interfaces. And that's all great. Seems to make a lot of sense. If you can upload things, like that's a reasonable method signature. If you can download things, that's a reasonable method signature as well. But the problem really comes when you have something like this. And that generate report function needs to take a client. That client needs a download and an upload function. So that comment there that says what type should go here is a really good question for what most would say small interfaces are the way to go. Because you can use the I can upload, but that allows things to be passed that would throw an exception on client.download. You can use the I can download, but that raises an exception when you get to client.upload. You can depend on the FTP client class itself, but because that's a concrete implementation, not an abstraction, what's going to happen when you want to upload your files to S3 instead? So the solution is, well, just have an interface that implements the two interfaces. So here you see on line 11, I define a new interface called the IFTP client. It implements the I can upload and the I can download. And then finally, my FTP client implements the IFTP client interface. All the way down there on line 31, I filled in that comment with an actual type, which is the IFTP client. And then everything is happy, you know? But once again, we have the issue. What if we want to upload reports to S3? S3 is not a special case of FTP, so it shouldn't be inherited from it. And more importantly, as we build on this, we're going to have a complex maze and hierarchy of interfaces. And I can upload could relate to a lot of different things. You know, it's not just uploading files, it could be uploading transactions to a database or something like that, or, you know, scripts to a database server, and they could have different access patterns. So while this works, and I'm not going to fault those that suggest this, Python definitely allows us to do this a little bit better. So in my words, interface segregation is about making reasonable decisions about how other developers will interface with your code. So that means interface segregation is more related to the I in API or CLI than it is the interface keyword, like I was just showing you. And I think that is where the readability counts from the Zen of Python comes in, because a good interface matches the semantics and terminology of the real world concept it is abstracting. So it makes for very readable code. And I think the example here, it can be the S3 client that I was referring to. It has the same upload download semantics as an FTP client, but to follow Liskov's, we don't want to inherit because this isn't an actual special case. So we're going to pull these out into their own interface, and we're going to use what Python, or the closest thing Python has, which is an abstract base class, because they are both file transfer protocols. And so we are going to define a file transfer client, which is our abstract base class. And instead of having upload, download interfaces or base classes like I showed in the C# code, we're just going to keep those under the file transfer client, because file transfer, you can upload and download. Like, it's still a single use case, and it's all still very related. So the code is still cohesive to structure it this way. It also allows us to put bulk FTP, or I'm sorry, bulk file transfer as its own abstract base class. And I actually have a bug in this code, and as I'm looking at it, I realize that it should be implementing the file transfer client. Otherwise, the upload download that I talked about earlier doesn't work. So I'll fix that later. But if we go ahead and structure our interfaces like this, there we go. We can actually get all of these different file transfer clients out of it. So we still have our FTP client, we still have our FTPS client, we still have SFTP client, but now we have our S3 client that I was talking about, and I even managed to squeeze in an SCP client because it can also do uploads and downloads. And you'll note there that S3 and SCP don't necessarily have to do the bulk file transfer if they don't need them. So now we finally get to the dependency inversion principle. And I think this is the one that's going to tie it all together for us real quick. So our formal definition is high-level modules should not depend on low-level modules. They should depend on abstractions. And abstractions should not depend on details. Rather, details should depend on abstractions. And I think that's a pretty confusing definition. So let's see if we can clear it up. My relevant Zen for this was explicit is better than implicit. And so a technique for doing dependency inversion is dependency injection, which most people are pretty familiar with. And you're just explicitly stating what something depends on rather than implicitly depending on it by constructing that thing inside of a constructor. So sorry, I'm reading my notes because I don't want to get this part mixed up because this is the really crucial bit. So the underlying file transfer protocol, we are no longer dependent on a detail, and that detail is the underlying file transfer protocol being used to move files around. And that detail is instead dependent on the access pattern defined in the file transfer client abstraction. And then by injecting objects that implement on file transfer client, we are allowing our high-level modules, those things that need to move files, to depend on the same abstraction, the file transfer client, and not a specific low-level module, which are the protocol-specific classes that we defined. So a quick example of dependency inversion using dependency injection is right here. And you'll see here all of those clients that I showed talking about interface segregation can be passed into the exchange function. The exchange function uploads the file, downloads it, and returns. And that, I think, is the true power of when you start using all of the solid design principles together. You have code that is that flexible and that powerful together. So concluding that, I'm not going to say that Pythonic is the same as solid, but the solid design principles definitely fall within the Pythonic ways of writing code. So clearly this was a curated example. I knew it was going to fit perfectly with everything that I was trying to present. It's something that I'd worked with a lot and is an ideal example, but it should demonstrate how all of those principles can work together to really make your code cohesive, loosely coupled, and just very powerful. There are also multiple ways that I could have gone about achieving a solid design principle in this example. If I haven't provided enough reasoning as to why I did each one, feel free to @ me on Twitter, send me an email, or of course, ask a question now.
I'll ask a question now if I could.
Sure.
Hey, thanks for taking my question. If you could go back to the slide of, I think it was it Lipshov?
Liskov's?
Liskov's, yes.
Okay. The slide or the
code? Now, when you, the word replace there, does that mean substituted for, or does it literally mean replace?
I think substituted for could.
In other words, they're functionally the same.
Yeah. So I think actually, let's go back to our last slide there. This slide. So. So let's switch this last slide up. If the exchange function was expecting an FTP client instead, and because SFTP client and FTPS clients inherit from that, you can pass those in as the client. It can still explicitly say that it is waiting for an FTP client, but because those are going to match the same interface, you can replace them or substitute them.
Yeah.
And so that's what it's referring to. I hope that explained it well enough.
Yeah, I think the word substitute for rather than, substitute for would be clearer than replace, because replace could suggest you could change essentially you're changing the meaning of what we understand by classes.
Okay. So this is the first time I've presented this talk. The article got a lot of attention on Dev2, but that is great feedback, and I'll definitely incorporate it.
Okay.
More questions? While everyone's thinking about their questions, let me ask something. Those came from C and C++, those solid principles, if I understand correctly. What actually breaks? Like, you showed some semi-examples of what's happening, but what does Python is quite different than what was originally thought of?
So the most difficult one for me to wrap my head around was the interface segregation principle, just because everybody explained it with the interface keyword, and like Python didn't have interfaces. And part of the inspiration for this talk is I know so many languages and I've programmed so many in them, and I've loved these principles and I've always carried them to each language. But when I got to Python, interface segregation specifically was the thing people told me all the time, well, that's not Pythonic. And I'm like, well, Python's not a real language, it should have interfaces. And so I calmed down a little bit, and I really thought through it, and that's where I came to the realization that it's not about the interface keyword.
Right.
Duck typing also alleviates, some of this. Like, there was a slide in here talking about the dreaded diamond of inheritance that C# and Java have to deal with, and I took it out because I didn't want to go too much in the weeds. Because the method resolution order and duck typing that Python offers allows you to kind of break the solid design principles in a way that they never truly expected you could, because those are all statically checked things that would stop at the compiler, and Python would just happily run along with them.
Okay, thank you. Andrew, you wanted to say something?
I was just going to say that I agree. You don't need the word interface to implement interfaces. The key, if an interface is a keyword, it essentially helps you enforce the discipline rather than you having to do it yourself. Yeah.
For me, that was the big, trip up for me. Once I finally realized it, I started liking Python a little bit more and could start writing solid code.
Right. For example, in C++, if you have an interface and don't implement one of the functions in the interface, you can't even compile the program. It's a very safety first type of set of rules. Whereas in Python, you could you could treat a class as an interface, which is what you're doing, and then not implement one of the methods because you didn't need it, for example. Even putting in a default, like just a return non-implemented return.
Yeah, and to that point, in this slide here where I'm defining the file transfer client, I'm passing ABC into it. I didn't use the abstract method decorators, which would actually enforce that a child implement this. And this is something that I can do in Python. I could have replaced pass with not implemented exception as well. And that's something that Python can do that these other languages can't, because there's no implementation that can actually go in an interface in C#, Java, C++.
Right.
So unless anyone else has questions, I'm gonna wait a few minutes or a few seconds. No more questions? Just unmute yourself and ask the question if you want to ask. Well, no questions for now. So what I'm gonna do is I'm gonna unmute you all, and all of you please clap for Derek for his presentation, and don't go away. We're gonna continue. So I'm unmuting you all, and please. Okay, I'm gonna mute you, put you all back on mute. Okay, so good. I'm gonna go back, and Derek, thank you again. We'll stay along. We have another presentation. Ivelin has been working on a home automation project. It's actually more of a company. He'll tell you more details. And in this talk, there is a connection to the epidemic that we're now experiencing. So, Ivelin, I'm gonna unmute you, and the minute I find you online here, I'm gonna unmute you. Here we go. Okay, and Ivelin, go ahead, share your screen, and hopefully we'll be, yes. Yeah, technology works sometimes. So Ivelin, without much ado, I'm gonna unmute myself, and you're gonna talk and present your home automation project.
Good. Thanks everybody for joining virtually. It was a lot more fun when we met in person last time, but it is what it is. And thanks Derek for that solid reminders of writing code. I need to see how much of my code will pass that test. Made me scratch my head as we were going through the principles. Sometimes we forget about these things. Okay, so briefly, my background, most of my career since graduating with computer science has been around open source projects, Apache, GNU, and various organizations and foundations. I've either been contributing or being part of companies that are building the business model around an open source project, JBoss, Red Hat, Telestack. So last summer, fall time, I started playing with some of these new home automation systems. And there are some really good open source ones that are coming along, and a bunch of popular ones that are out there, NetString, Alex, all kinds of good stuff. And what I noticed is there is a lot of promise, obviously, with a lot of AI implementations and modules and models coming together, being really useful, not just fluff, but actual working stuff. However, I had a little bit of problem with the way that privacy and user data is handled. So looked around for, of course, open source implementations. I couldn't quite find a fully baked system, but I found that many of the building blocks are there. And I started putting them together and put a name on the project. So essentially, the goal is to see what's the way that we can leverage open source building blocks to build something that's intelligent in the context of home automation, but also preserves privacy. You don't have to trust it that it doesn't trick you what happens with your data. It's not uploaded from some strange cloud account and it's either sold or leaked or hacked or something like that. Most of you are pretty familiar with this. Most of you probably have more than one home automation system, so I don't have to talk about that. And you're well aware that it's a growing market, mostly driven by AI, with a lot of the different aspects of home automation becoming more intelligent. So, but the problem again is privacy. So what I tried to do is put together something that addresses privacy on all the layers that I could think about, which are the AI piece, so inference and training, would happen, of course, on user data, but that data never has to leave a user-controlled device, whether it's at the house or a mobile device. The data, or even if it's a server, doesn't matter where it is, but it has to be user-controlled. Not on paper, like a lot of cloud accounts would make us believe that, hey, it's your data, you control it, but it's really our servers. So there is pages and pages of legalese what actually happens with that data. So see if that's possible on the AI side. It also with storage. And then if data has to be transported between user-controlled devices, it's done in an end-to-end encrypted way. So as a mission, let's try to do this as easy as possible and preserve privacy and not require any cloud accounts to log in to get things done. One thing that kind of frustrated me with Nest a few months ago was that the Nest camera is that to get the data out of the Nest camera, I can't really plug into the RTSP stream of the camera. I have to go get an account, Google Cloud account, and I have to go get my own data from Google Cloud. The data is coming from our house. That makes no sense to me whatsoever. So fortunately, there's all kinds of cameras out there that are commodity with basic RTSP stream that you can get it and keep it in the house. So that's kind of the three steps that I try to address. Run AI locally, store things locally, don't collect from the cloud, don't use user data. Whatever user wants to do their data, it's their problem, their choice. And when they communicate, it's peer-to-peer, no man in the middle servers. And I'll kind of bring this into an actual use case that is hopefully easy to relate to. We've been pulling to multiple hackathons. Jacob actually mentioned about one a couple of weeks ago, and then there is another one this weekend, and then another one 2-3 weeks from now that are college-related hackathons. But the use case that we're working on there is fault detection. So essentially, you see here the 4 steps of the system. Camera in the house is obviously able to see what's in its vision scope, and then over a local RTSP stream, the data goes to a local Raspberry Pi or not some sort of local device that runs the inference, detects person, object, faces, motion, and things like that, whatever makes sense. And then it streams it over peer-to-peer, over WebRTC data channel to a PWA mobile app. Where this is being used now, and we have some these tweets actually from real users, is they're using it to keep an eye on elderly that are isolated in their houses and are not able to receive daily attention from the medical team or family members that are typically there to check on them. With something that's open source and completely transparent, they can keep an eye on family members without having to sacrifice privacy. So let me jump into the Hello architecture, and then I dive into the Python piece of it. There are three main layers. I mentioned them earlier. The front end is a progressive web app, Vue.js, all JavaScript, connects our WebRTC to the edge device, which is mainly Python code that uses TensorFlow, TensorFlow-Lite, GStreamer for the RTSP camera inputs, and the pipe for local storage. It also uses a new, relatively new WebRTC Python implementation called IRTC. I'll mention that in a little bit, which turned out to be pretty useful. Physically, that's what I got running in my home, an outdoors camera indoors, and a pipe next to a common system, which many of you probably know. Okay, so the UI, I'll switch to the next tab to give you a sense of what I'm running in my house. The UI is essentially a reverse chronology timeline, kind of similar to a social timeline, but with your private data. In this case, what's happening around my house. My son running around earlier in the day, maybe about half an hour ago, was detected running. And because there's a person detection, the next model in the pipeline zoomed in to see if there's a face detection possible, and that's what it got, just the person. There's not enough to detect the face, but stuff like that. That's what this is, the other kids running around. And if I keep scrolling, it'll show what's coming from deliveries from Amazon and stuff like that. So let me switch actually to the front end, but I'm gonna switch to another tab that actually has some sample codes from the edge device too. So one of the side effects of, I'm not sure how many of you are familiar with WebRTC, but one of the side effects of WebRTC is that it's possible to do sort of airdrop-like discovery between two devices, really kind of plug and play discovery. Just by having a mobile phone on the same local network as the Raspberry Pi, they can, at that moment, they typically share the same public IP address, which makes it possible for them to discover each other through WebRTC signaling. And that kind of skips a lot of typical steps for peer-to-peer connectivity that normally involve setting up VPN, setting up dynamic DNS, static public address mapping, port forwarding on the router, home router. A lot of these steps are completely transparent with WebRTC discovery. Another thing that also turns out to be a nice side effect with this WebRTC approach is that because there is an end-to-end encryption, and each endpoint is able to generate its own unique UID4, crypto-safe identity, and authenticate with each other. There is no really a need to go through some sort of server or cloud account for identifying the device. It's possible to do that just based on the fact that they're allowed to share for a moment the same local network. So the fact that they were allowed to join the same local, let's say, Wi-Fi and other credentials is what enables an initial handshake. And from there on out, they can find each other based on that UID4 and communicate remotely even if they're not on the same network anymore, over the channel in this case. I'll skip the JavaScript part because that's not the point of this meetup. On the server side, something that that I implemented, I think is useful for folks that are looking at peer-to-peer secure discovery communication, is a port of a Peer.js project. It's pretty popular for browser client-side WebRTC library, but I didn't find one on the Python side. So I ported it and implemented a simple HTTP proxy, which effectively makes it possible for browser apps to connect to an edge device agency plus a cloud-hosted server. So normally from a browser you would use XML HTTP request or a fetch API function and gather its source from the cloud, from web server. But if you think about it, how would you do that if the server is behind a private firewall? Like, how would you get that? In some of the typical ways, okay, I see that there's chat question. And some of the traditional ways that has been done is through setting up VPN and dynamic DNS and getting certificates for a dynamic DNS that maps to a private IP. It's pretty brittle and it takes quite a few steps, which for a user, I thought it was a stretch. Okay, let me see, look at the question. Oh, sorry. So, yes, okay, John Krasnowski, good question. So that kind of depends on the Wi-Fi router. If the guest account ends up sharing the exact same public address as your native.
Ivelin, please repeat the question. Some people on chat see it, some don't.
Okay, so the question is, would someone logging into a guest account on the Wi-Fi also be capable of accessing the data? I'm on a computer without video microphone. Okay, cool. So that's the question. And so the answer is, it's a good question. Depends on the Wi-Fi router. If the guest account ends up sharing the exact same public address and is seen as a native member of the Wi-Fi group, then yeah, it would be able to see the rest of the devices. So because of that, it might make sense to add additional layers of authentication, like for example, when setting up the Raspberry Pi device, the user may set up an admin user account and password, so that if a guest device tries to kind of hijack plug-and-play connection and connect without asking for permission, that extra layer of security would prevent it. And there are other techniques for additional authentication of devices once they find each other, to make sure that they're not doing something they're not supposed to. In the initial version, it's pretty straightforward. It's pretty much Bluetooth plug and play, right? There is no this extra layer of security. The assumption is that they're close enough, physically close enough, that already is a level of trust that most devices don't have with each other. Okay, I don't see other questions, so I'll keep going. And I feel that I'm running out of time, Jacob. It's 8 o'clock, so call me out.
You're fine. Continue. The Python is interesting.
All right, I'll try to speed up. So just to finish my thought here, this whole problem of how do you connect web browser to devices on the edge that are behind private firewalls and are not publicly accessible web servers, that's one solution, right? There are these PureJS libraries, Apache is freely available out there, and now there is a Python version of it that symmetrically can connect to these web apps and pretty straightforward. So I think from there, PHP proxy piece does exactly what the name suggests. It translates WebRTC data channel requests, which is kind of low-level packets, into HTTP proxy requests to something that's running on the Pi. So if your application sort of has a REST API on the Pi, the web app will be able to work with that through this WebRTC layer. Right. This thing is a reference. It's a public article. It's available. I don't think I'll go through all the steps here. So I mentioned earlier that AORTC is a relatively new Python project, but it's getting quite a bit of attention. There is also a Go implementation of WebRTC now. But the biggest news actually is that as of late 2019, all the major browsers have very decent implementation of WebRTC. That the standard has been in the making for almost 10 years, and 1.0 was finally released the RFC like middle of last year, late last year, along with all the browsers saying, okay, we finally supported Safari, Firefox, Chrome, Opera, all supporting it. And I personally tested and I was surprised that it finally works well. On the AI side, there is probably a topic for yet another discussion, but currently running very simple TensorFlow Lite with pre-trained models, and there is a sub-project that I welcome anybody who's interested to talk to me offline about it. We're trying to bring in federated learning into this project so that users can train the model without having to share any data. But that's kind of a bigger topic. Okay, I probably can wrap it up here, Jacob. We're running kind of past 8 o'clock, and if there are questions, we have to answer.
Okay, I say thank you, and you can continue a bit more because like we're a bit online, we have a bit more flexibility in time, but I guess some of the questions may be leading you to some of the things you haven't shown before. So I have several questions, but maybe I'll start, but if someone else has a question, feel free to unmute yourself and ask directly. If you cannot, then put it in the chat and we'll ask it for you. So the question that I have is two things. Actually, I have several of those, but the first one is you're showing Raspberry Pi and then you're showing on it TensorFlow. This is something like TensorFlow usually requires quite a bit of computing power, usually. Raspberry Pi is strong enough to run those models, and like, what's your experience with this? Tell us.
Yeah, I was very curious as well. So what I found out is it's a very dynamic field. What I started testing 6 months ago is probably 2-3 times less efficient than what's available now. I think I started testing on TensorFlow 1.11 or 12. The current models are on 1.15. I haven't moved to 2 yet because TensorFlow 2 is not quite as stable. TensorFlow Lite, the 2 branch is not quite as stable as I'd like it to be. I'm a contributor to the TensorFlow 2 branch, TensorFlow IO, and try to keep an eye on how things are developing. But as it relates to Raspberry Pi, with the latest efficient net, even mobile net 2 models, I'm able to run 2 cameras with between 1 to 2 frames per second, where each camera has 2 model sequences. One is for object detection, another for face detection. The inference for each is between 400 to 500 milliseconds. If I plug in the coral, which you can see on this picture in the lower right corner, if you plug in, no, that's on the coral, where'd it go? It's out of the picture. But if you plug in the coral, the inference drops to 40 to 50 milliseconds, so it's 10 times faster just for inference. Overall, it improves maybe 20–30% because a lot of the CPU is consumed for RTSP H.264 decoding. So to me, the Pi4 is pretty powerful. It can do a lot of useful things, and it still has some CPU left to do local training when we plug that federated element in it.
So you're actually saying that the Raspberry Pi not only can run the model, it actually can train?
So I haven't done enough training, gotten results to comment yet. But in terms of running inference, I've been pretty happy with this. It's been running on 4 weeks without downtime, with something like running MobileNet 2 4 times a second.
This is nice.
Pretty decent. Pretty decent.
Pretty nice. And it's all in Python.
My code is Python. TensorFlow has by default a Python layer. It has JavaScript and all kinds of different wrappers, but most of it is C++.
Interesting.
I don't work with that most of the time.
Okay. Any other questions from anyone in the audience? Otherwise, I'll ask one more. I'm going to mute yourself for a second, but go ahead, unmute yourself. Give some. Okay, it seems that people are either shy or looking for the unmute button, which is possible also, those new systems. So I'm going to ask one more question, maybe someone else. So I know you've done some work with this, something called TensorFlow IO, TFIO. Can you elaborate on this a little bit more and explain what's it good for and what will be in the future for that? And how does Python come along?
So one of the things that I'm curious about is how do we skip the part where we do a lot of work to decompress video stream into a raw image, then run it through an image model to detect something in it. It's still a lot of work in progress, but the intuition is that there is a lot of motion already encoded in compressed videos that already tells us the motion vectors. So in theory, we should be able to reuse a lot of compressed data that tells us about objects, about motion in the video to feed directly into a model. So one of the first steps in that exploratory journey is to actually get raw video data into TensorFlow. And there is a subproject of TensorFlow called TensorFlow IO that deals with that. The team is working on bringing all kinds of different native formats straight into TensorFlow graphs. And contributing to that team and wrote one of the articles that are on the homepage of how you approach that problem. If anybody's interested in getting data from this specific example that I give here is with network PCAP data. That's my first iteration of how do we get raw network data that already includes latency and jitter buffer errors, and use that for media correction, voice correction, and or video correction. So that was one of the projects I was playing with. So now it's possible. There's a way to do that with TensorFlow.io. But of course, that's one piece of the equation. Then you have to go through, build a model, design an architecture of a model that can deal with that type of data, which is still not there.
Well, thank you for the answer. If someone else has a question now, then now's the time. Otherwise, I will ask one last thing and saying, is there anything else you want to highlight for us to remember? But wait a minute, maybe someone will come up with the question. But if not, go ahead and tell us one thing you want us all to remember that you can do maybe with Python that no one else can do currently.
Oh my goodness, that's a tough one. I think I found curious that there is not yet a bridge, peer-to-peer bridge between browser and Python apps, and now there is one. So hopefully we'll see some use for it.
So you provide a bridge directly through a Python app without a browser in the middle, correct?
From browser to Python without a public web server in the middle.
Ah, okay. Thank you for the correction. Okay, so if no one else asks a question, then I guess we're gonna unmute everyone again and ask everyone to please clap and thank you. So I unmuted you all. Hopefully you're all unmuted, and I will give you a clap.
Okay.
And I'm gonna mute your backs before we get all those funny noises.
I'll mute too. Thank you, Jacob.
Okay, thank you very much. I'm gonna be posting this video online later on. I'm gonna stop the recording now.